Okay, we want to look at two proofs in section 9.5 on alternating series. We did a lot of examples in the class, but we didn't go through the proof. So some of the notation in the proof of the alternating series test gets kind of hairy. So what I want to do first is look at a specific example. So then when we do the generic proof, you can relate it back to this. So as a specific example, let's consider the sequence an is 1 over n squared. And we're going to form the alternating series from that. So remember in this section, specifically when we say an, that's the positive term series sequence in the series, and then the negative 1 to the n plus 1 is taking care of the alternating part. Normally when we write a series sum of an, we don't necessarily assume the an's are positive, okay, but here we are. Okay, so we have this series and it's alternating. So let's just list first the elements of the sequence of partial sums, and I want to break it up. Notice I have S1, S3, S5, so those are the sequence of partial sums with odd subscripts, and then I'm going to look at S2, S4, S6. So I'm going to do them as I work, I'm going to do them simultaneously, then we want to look and see what we have. Okay, so we're starting with n equals 1. So S1 is what you get when you plug in n equals 1. Well, when n is 1, negative 1 squared is positive 1. And then 1 over 1 squared is just 1. Now, how do you get S2? S2 is the sum of the first two terms of the series. Well, we already know the first one is 1. And when we plug n equals 2, you're going to get negative 1 cubed, so that's going to be negative. And then when you plug 2 into here, you get a fourth. And I'm not going to simplify. All right, so S1 is 1, S2. And of course, the terms are going to alternate plus, minus, so I don't really need to plug into that part anymore. Now let's go to S3. S3 is going to be these two terms plus what we get when we plug in 3, and so that's going to be a plus from that, and then 1/9. And then when we go to S4, it's those three terms minus, when you plug in 4, you get a 16th. We'll do two more of these. Then S5 is S4. Right? But then you have to add what you get when you plug in 5, 1 over 25. Okay, last one, S6 is going to be S5. And then minus what you get when you plug in 6, which is 1 over 36. Whew. Okay. Okay, so again, those are all written out in the notes there. That's where they're coming from. So remember, S6 is the sum of the first 6 terms, right? S5 is the sum of the first 5 terms. S1 is the sum of the first term. Okay, so there we have it. Okay, so I say note, I want to compare some of these. Here, S2 is S1 minus A2. Okay, so here's S1. If I subtract A2, I get S2, right? There's the minus. Remember, A2 is the positive term, just the 1 over n squared, right? So S2 is S1 minus the second term. And again, plugging in 2 into there. A sub 2 is a fourth, right? Likewise, S4 is S3 minus A4, isn't it? Okay, so here's S4. So there's S3 minus the fourth term. A sub 4 is 1 over 4 squared is 1 over 16. And likewise, S6 is going to be S5 minus A6, right? So here's S6, there's S5 minus A6, 1 over 6 squared. Okay, so that's what I want you to notice from this specific example. And we're going to call this sequence, so the sequence of partial sums is S1, S2, S3, S4, S5, etc. But we're going to focus on the odd subscripts and then the even subscripts. So this is what's called a subsequence, right? Whenever you have a sequence and you just pull out certain terms and keep going, that's called a subsequence. So so S2n. S sub 2n is the sequence of even partial sums. Notice when n is 1, you get S2. When n is 2, you get S4. When n is 3, you get S6. And the sequence of odd partial sums, they are going to denote 2n minus 1. S sub 2n minus 1. Notice when n is 1, you'll get 1 for the subscript. When n is 2, you get 3 for the subscript. When n is 3, you get 5 for the subscript. Okay, so this is the key relationships we want to focus on here. Okay, so let's do the proof of the alternating series test. I think I may need this whole board. Okay, so keep those relationships in mind. We're going to need them eventually. Okay, so we're going to assume the limit as n goes to infinity of a n is 0. That was the first assumption in the alternating series test. And we're going to assume a n plus 1 is less than or equal to a n for all n greater than or equal to 1. Okay, so those are the only two assumptions in the alternating series test. Now remember, the a sub n, the a sub n is referring to the positive part in the alternating series. Okay, so we're assuming that. Okay, now let's focus on the sequence of partial sums with even subscripts. So we're looking at the sequence S2n. So S2, S4, S6, S8, etc. Okay, so let me start writing down some terms. So S2 is A1 minus A2, right? It's the first term minus the second term. Okay, because I'm assuming the series alternates plus minus plus minus. So it's plus A1 minus A2. And let's look at S4 is A1 minus A2 plus A3 minus A4. Okay, remember the first four terms, A1, A2, A3, A4, and we're assuming the series alternates plus minus plus minus. And let me write, now what would S2n look like, the generic term? It'd be A1 minus A2 plus A3 minus A4, etc., plus dot 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 plus. Now think about S2 ends at A2, S4 ends at A4, so S2n is going to end at A2n. And notice it's going to have a minus in front of it, right? Because they're paired up here, right? Plus minus, and so the last two. Now, what's the term right before this? It's going to be A2n minus 1, right? Right before the last term, you subtract 1, so that's 2n. That's 2n minus 1. All right. Now, notice I put parentheses around these terms like this because I want you to notice something here. Okay, so remember we assumed that an plus 1 was always less than or equal to an. Right? So what if I subtract an plus 1 from both sides? I'll get zeros less than or equal to an minus an plus 1. Right? Subtract an plus 1 from both sides. You'll get a 0 here and an minus an plus 1. Right? So if we assume this is true, this is true. So if you have consecutive subscripts here, where the second one's one bigger than the first one, that's non-negative, right? You're not going to get a negative number out of that. Right? So what they want you to notice here is here's S2, right? Right? That's non-negative. A1 minus A2 is bigger than or equal to 0. So that's a number bigger than or equal to 0. This one we just argued, that's bigger than or equal to 0. But A3 minus A4, that's bigger than or equal to 0. Same argument. Same thing here, all the way down to same thing here. Right? Right? So how does S4 compare to S2? Well, these are the same, but notice you've added something that's not negative. It could be 0, but it's not negative. So S4 is going to be greater than or equal to S2 because you're adding either 0 or a positive number to S2. Now keep going. How does S2n compare to the one right before? Well, the one right before is going to have all these terms through here, and then you're adding something again that's greater than or equal to 0. So notice this sequence of partial sums that have the even subscripts, it's non-decreasing. Okay, if you found S2 and S4, S6, S8, etc., and kept going, the one below is always going to be at least the one above because you're always adding something that's at least 0. So notice this shows that S sub 2n is non-decreasing, meaning it's monotonic. So all this is just to show S2n is monotonic. Right? Remember, non-increasing or non-decreasing, it means monotonic. Okay? So all this argument is for. Now notice what we needed. We needed this condition right here to argue that S2n was monotonic. That's where that's coming into play. Okay, now let me go back to this again. Okay, I messed it up. Ugh. Okay, let me write S4 again. And let me do S6. And now what's S2n? I mean, I'm going to explain what this is doing. Hold on. A1 minus A2 minus A3 minus, goodness gracious, A4 minus A5 minus dot 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 minus A2n minus 2 minus A2n minus 1 minus A2n. Oh, I ran out of room. Oh, you can see that. Okay. Okay, so notice we've rearranged parentheses here. Now be careful. I know you say, wait a minute, there's a minus and a minus and a minus. But if you distribute the minus sign, notice it's A1 minus A2 plus A3 minus A4, which is exactly what S4 is. And then A1 minus A2 plus A3 minus A4 plus A5 minus A6. Same thing down here, right? A1 minus plus minus plus. Then you'll get minus plus, minus plus minus. Okay? So notice for the even, A2 has a negative, A4 has a negative, A6 has a negative. A2n is an even subscript, so that will have a negative. Okay, so we rearrange the parentheses and we factor out a minus sign. Okay, so we want to use the same fact that we did before. Okay, remember an minus an plus 1 is greater than or equal to 0. Okay, so let's look at S2. So we've started with A1 and we've subtracted A2 from it, right? From this. That's greater than or equal to 0. Same thing as before. Okay. Right? But since A2 is positive, right? A2 is positive, but it's less than A1. This number's less than A1. That's not, I don't really care that's positive. Right? The key here is I want this, this is going to be bigger than or equal to A1, isn't it? No, it's not. Sorry. It's less than or equal to A1. Right? You started with A1 and you subtracted a number, a positive number, A2. The A sub n's are positive. A1 minus A2 is less than or equal to A1, isn't it? Now let's look at S4. Here's A1. I'm subtracting A4 from it, so I'm getting smaller. Notice A2 minus A3 is non-negative. So I'm going to subtract a non-negative number from A1 as well. So you have A1, and you're subtracting a non-negative number from it, and you're subtracting another non-negative, a positive number from A1. So this is going to be less than or equal to A1, isn't it? And you could use the same argument all the way down, right? Here's A1. I'm subtracting a non-negative number from it. I'm subtracting a non-negative number from it, etc. I'm subtracting a non-negative number from it, and then I'm going to subtract a positive number from it. So this whole thing is going to be less than or equal to A1 as well. What's the worst case here, right? Worst case is this is equal to 0, right? And suppose that were equal to 0, all of them. That would be 0, that would be 0, that would be 0. You'd have A1 minus 0, minus 0, minus 0, minus 0, minus a positive number. You're going to still be less than A1. Okay? So you could do this argument all the way down. So notice what we have shown here, and we know that these are going to be greater than or equal to 0. This shows that the sequence S2n is bounded above by A1. Right? Every single one of these terms, S sub 2n, is less than or equal to 1. Okay. And again, from what we argued before, right? Because this is true, the way I had it arranged before is going to be bounded below by 0. Okay, I already erased that, but look at what we did before. Every single one of those terms, when I had A1 minus A2 plus A3 minus A4, grouped that way, every single one of those was greater than or equal to 0, right? So the way I had it before, well, let me just write S4. S4 was A1 minus A2 plus A3 minus A4, and we grouped it this way. That's greater than or equal to 0, that's greater than or equal to 0 from this. So the sum is greater than or equal to 0. That's true for all the Sn. So we're bounded below by 0. And remember, we had a theorem that said if you have a monotonic sequence that's bounded, right? This is bounded above and below, so bounded. So this tells me that S2n converges. And let's just make up a number to some number L, capital L. So all this work, the two ways of writing it, the first one we explained, you know, the grouping that I did in the first place was to get monotonic. This grouping was used to show that we're bounded above by A1, and again, the first grouping we did explains that we're bounded below by 0. Okay? So all that work was to show that S2n converges to some number L. That's what all that was for. Right? And notice I just use this fact, I use this fact over and over. An plus 1 is less than or equal to an for all n. Notice I haven't used the first fact yet. Okay? Now, remember the fact we listed above? I said S2 was S1 minus A2, S4 was S2 minus A4, S6, not S2, S4 was S3, and then S6 was S5 minus A6. What's the general pattern here? Notice these are all the even subscripts on S, those are all the odds. So S2n is S2n minus 1 minus an. That's the pattern we have there. Right? S2n is 1 less than that, 1 less, minus the same 2n. Same subscript, right? That subscript and that subscript are the same. And that subscript is 1 less than that. Okay? Let me solve for S2n minus 1. So S2n minus 1, if you add A2n to both sides, you get S2n plus A2n. Okay? So let's take the limit. So notice this is all the s's with the odd subscripts, which we haven't dealt with yet. We know what the S2n's, the even subscripts, if you just, so we have this sequence. We have S1, S2, S3, S4, S5, S6, etc. If I just take the even subscripts and ignore the odds, so look at the numbers S2 and S4 and S6 and look at that pattern, those numbers are going to start heading to the number L. The question is, what do the odd subscripts do? That's what we're trying to figure out. We know what the even, the S2, S4, S6, if you go out to infinity, those numbers are getting closer and closer to L. We know nothing about the odds. But here we have a relationship between the s's with odd subscripts and the s's with the even subscripts. Let me take the limit of both sides of that. The limit as n goes to infinity of S2n minus 1 is the limit of the right-hand side. The limit as n goes to infinity, I'm going to break it up. S2n plus the limit as n goes to infinity of A2n. Well, I just said, we already proved this. When n goes to infinity, what happens to S2n? We said S2n converges to L, so that sequence goes to L plus. Now, notice this isn't A sub n, it's A sub 2n. So let me use the same argument there. We have A1, A2, A3, A4, etc., A5, that's a sequence. Well, what do all those A's go to? Right now I'm using the first fact. As n goes to infinity, this sequence heads to 0, right? That goes to 0, the whole sequence. Well, if the whole thing is going to 0, what are the even subscripts going to do? A2, A4, A6, etc. If the whole sequence is heading towards 0, the even subscripts have to go to 0 also, right? If the even subscripts shot out to infinity, the whole thing couldn't go to 0, right? So this limit turns out to be 0, and L plus 0 is L. So notice what we showed, right? We showed the sequence S2n converge to L. This shows that the sequence of S odd subscripts also goes to L. Right? So if I go back to my S1, S2, S3, I knew all the evens went to L. I just showed all the odds would go to L. So half of those terms go to L, the other half also go to L. the whole thing is heading to L. And so notice this is the sequence of partial sums for my alternating series. They converge to a number. Remember, the definition of a convergent series was a sequence of partial sums converges. So we just showed the sequence of partial sums converges to L, which means my series converges, and that's what we were trying to show. So if you have these two facts for an alternating series, the series converges. That's what we were trying to show. So it's a lot of manipulation, but it works out beautifully. And notice we only had to consider the sequence of partial sums with even subscripts. That took all the work. Once we had that, the odd just popped right on out. Okay, then the second proof in this section, which is much shorter, was trying to, the alternating series remainder. Okay? So remember, if you had an alternating series that looked like this, n equals 1 to infinity of minus 1 to the n plus 1 a sub n. Again, the a sub n's are positive. It doesn't have to be minus 1 to the n plus 1. You could use minus 1 to the n and use a similar argument. So that's a1 minus a2 plus a3 minus a4, etc. Okay. And remember what the remainder says. Let me put, plus a sub n minus a sub n minus plus 1 plus etc. Right? What it says, if you add up the first n terms of an alternating series and use that to estimate the actual sum, it's certainly not going to be equal to that unless all the terms after are 0. Right? Okay, so if you add all these up and use that as an estimate for the sum of the total sum of the alternating series, you are what's the error you are away? This is an approximation, that's exact value. The error, the remainder, the absolute value of the remainder is less than or equal to the next term, an plus 1. Just ignore the minus sign. It's a great little theorem here. So if you add up the first 100 terms, how close are you to the true value? The difference between your estimate and the true value is no more than the first term you didn't use. That's what we want to prove. Okay? Okay, so suppose we do that. They're calling this r sub n, the subscript meaning the last term that you added. All right? So notice Rn here is S. Now they're letting S be the whole sum, right? So they're calling the whole thing S. So they're saying S minus Sn. I mean, look at the picture here. S stands for the whole sum. This is S sub n. So S, the whole thing, minus S sub n is, that's what they're calling the remainder. Okay? So the Rn they're saying is this whole thing, the tail. Okay? So Sn plus Rn is the tail. If you subtract the total minus Sn, you get the remainder term. Okay, that's what they're saying there. Okay, well, what would that be? Well, S is the whole thing. N is 1 to infinity of minus 1 to the n plus 1 an. Minus, now what's Sn? Sn is the sum. N equals 1 to capital N of minus 1 to the n plus 1 an. Right, so again, S stands for the whole series, 1 to infinity. If you go from the first term to the capital Nth term, it's a sum from 1 to capital N of the series. Now think about what that is, right? Right? If you go from 1 to infinity and you subtract off the first n terms, notice it's just the tail, right? That's all this is the tail, right? We just said R sub n is the tail. And so that is going to be the sum of n is capital N plus 1 to infinity of minus 1 to the n plus 1 a sub n. I don't know why we went through all that work to get that. Right? We just said the remainder is the tail, and so here it is. You start with n plus 1. Right? This is a n plus 1. That was a lot of work to get to that. And then we start expanding here. So if little n is capital N plus 1, notice you get negative 1 to the capital N plus 1 is n plus 2, an plus 1. Right? Capital N plus 1, put it in here. N plus 1 is n plus 2, and that's an plus 1. And then the next term is going to be plus. You put in capital N plus 2, you're going to capital N plus 3, minus 1, to the n plus 3, a sub n plus 2. and you keep going, let me do one more here, it's in the notes. That's negative 1 to the n plus 4, a sub capital N plus 3, etc., plus dot dot dot. Okay, so what they say here is, you can factor a minus 1 to the n out of all those terms. Factor out minus 1 to the capital N term. I don't think that's right. We want to factor a negative 1 to the n plus 2 out of that. Yeah, capital 1 to the n plus 2. Okay, so it's not negative 1 to the n, it's negative 1 to the n. Wait a minute. Well, let me just do the n maybe and see what we get. Yeah, that's fine. Okay. I was trying to pull out the greatest common factor. It turns out, I guess it doesn't matter. Okay, so notice if I factor out a minus 1 to the n out of the first term, notice you're left with a minus 1 squared, which is 1. So you get a sub n plus 1. Right? Okay, and now if you factor out a minus 1 to the n out of this term, you're left with a minus 1 cubed, which is a negative 1. So you get minus a n plus 2. And then if you factor minus 1 to the n out of minus 1 to the n plus 4, you're left with negative 1 to the 4th, which is positive 1. So you get a n plus 3. And you see the pattern here. That way we don't have to have a negative 1 to a power, on every term. Now we pulled it out front. Okay, so that's where we are. All right, let me continue up here. Remember, that was Rn. So Rn, where we are now, Rn is negative 1 to the big N times an plus 1 minus an plus 2 plus an plus 3 minus an plus 4, etc. Plus dot dot dot. That's where we are. Okay. All right, we're almost done. That was way too much work to get there. Okay, so what they want to do is do the grouping, the same sort of game we did before with the grouping, an plus 1, and now let's put a minus sign in front of those two, so you get an plus 2 minus an plus 3. Remember the grouping we did before? This is the same game we're playing. That's minus an plus 2 plus an plus 3. And then do the same thing for the next two terms, an plus 4 minus an plus 5, etc. So notice it's minus an plus 2 plus an plus 3, minus an plus 4 plus an plus 5. So the pattern continues. So you pull off the first term, then you group the two after. Now remember, the assumption, we're assuming we have an alternating series, so an plus 2 is bigger than an plus 3. We're assuming the terms of the sequence get smaller. So notice that this right here is bigger than or equal to 0. This right here is bigger than or equal to 0, etc. forever. And so notice what you're doing here is an plus 1, you're subtracting a non-negative number from an plus 1. You're subtracting a non-negative number for an plus 1, etc. Right? So notice if we take the absolute value of Rn, notice I just said Rn here, I didn't put absolute value. That disappears. Absolute value minus 1 to the n is 1. And notice, right, so that's gone. And we just argued that you have an plus 1, you're subtracting something, or it could be 0, you're subtracting a non-negative number from it, another non-negative from it, So this is going on being less than or equal to an plus 1. It's that same argument I used before to show that S2n was bounded by a sub 1, right? You have an plus 1, you're subtracting something non-negative from it, etc., 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 so it's going to be less than an plus 1. And that's what the theorem says, right? The remainder, the absolute value of the remainder is less than or equal to the first term that you don't use in your approximation. So there's that proof. So there's the proof, the two proofs for the sectional alternating series.